Jai Hind to all of you. My name is Dr. Ritish Kumar. I am going to present a lecture on the topic of MOSFET, which lies in the subject of electronic device. The code of this subject is BEC 301. MOSFET is nothing but a metal oxide semiconductor field effect transistor. So this is the syllabus of the university syllabus. The MOSFET lies in the unit number 5. As you can see, this is a MOSFET. So uh, we will focus on this topic MOSFET in the further slides. So these are the recommended books uh, according to the syllabus. So I will recommend first two books for to study this topic. So MOSFET, as you can see, MOSFET is a metal oxide semiconductor field effect transistor. It is a kind of voltage control device, also known as IGFET, that is insulated gate field effect transistor. So MOSFETs, the other name of the MOSFET is IGFET. So if we compare the MOSFET with the BJT, there is some certain differences in the BJT is a bipolar junction transistor. So the conduction or current flows due to the both charge carrier, either the majority carrier or minority carriers. While in the case of MOSFET, only the current flow due to the presence of the majority carrier. So we can say there is no concept of leakage current in the case of MOSFET, while the leakage current present in the BJT. Due to the presence of leakage current, BJT has has very high noisy device, while the MOSFET is a less noisy device due to the absence of leakage current. Right. So in terms of bandwidth, also we can say it has large it has a large bandwidth, hence signal reconstruction is excellent. I will focus on the topic of MOSFET. So MOSFET has 4 terminal device. It has the terminal names is source, drain, gate and body. Body is also known as substrate terminal as well. So now the next I will discuss the types of the MOSFET. So you can see the types of the MOSFET. The MOSFET can be categorized in 2 types. The first one is the depletion type, and second one is the enhancement type. It in both types we have N type and P type, depletion type and enhancement type MOSFET. So as you can see, depletion type MOSFET in the depletion type MOSFET channel is present, while in the enhancement type MOSFET there is no channel present. So, you need to form a channel with the help of voltage. So these are the symbolic representation of depletion type MOSFET. You can see this is a N type MOSFET, and this is one is P type MOSFET, uh, P type depletion type MOSFET, and these are the symbolic representation of enhancement type MOSFET. Here you can see this is a dotted line which representing the enhancement type MOSFET. There is no presence of channel. We need to create a channel with the help of applied voltage. So you can clearly see here the symbolic representation. It is this is a very important symbolic representation. So now let's begin with the topic of depletion type MOSFET. As we discussed in the last slide, it has N type and P type channel, N type and P type depletion type MOSFET. So you can see here the first one is the N type MOSFET and second one is the P type MOSFET, right? So in N type MOSFET you can clearly visualize that we have taken the P type substrate, while in the P type MOSFET we have a N type substrate. So whatever we have learned in the case of P type, just do the replica or just do the opposite in the N type MOSFET. So you can see here depletion type MOSFET we already discussed, it channel is present in the case of depletion type MOSFET. So because the current flow the current flow due to the presence of channel in between source to drain. If you look in the construction point of view, this is a substrate. These two are the these are this one is the drain, this one is the source, and this one is the gate terminal, and this one is the substrate terminal. Also we call this is a body terminal as well, and this one is the channel. So in depletion type, channel is present, already present in the picture. So apart from this, you can see this is a symmetric kind of structure. You can change or replace source or drain, source with respect to source with drain and drain with source, uh, due to which we can say this is a kind of symmetric structure, right? So why we call this is a n-type depletion type MOSFET, because here the channel is created n-type, channel is present in the n-type. So that's why this device is known in terms of type of channel. If the channel is p-type, then you can say p-type depletion type MOSFET, and if the channel is n-type, then you can call the n-type depletion type MOSFET. So in the text you can clearly see here, for the n-type channel is n-type, for the p-type channel is p-type, source and drain is n-type, and in the p-type source and drain is p-type. So from the figure you can clearly see here, right? Now enhancement type MOSFET, as we discussed, in enhancement type MOSFET there is no uh, presence of, there is no channel already exists. So you can see in the previous slide channel is present, in the enhancement there is no channel in between the source and drain, right? But in the case but for the n type enhancement type MOSFET, we need to take the substrate type is p type, while for the p type MOSFET we need to take the substrate type is n type, right? And it has a 4-terminal device, as I discussed earlier: the source, gate, source, drain, gate, and the fourth one is a substrate terminal, right? So the this is a enhancement type MOSFETs construction diagram, yeah, or structure you can see. So let's begin with the topic of n channel enhancement type MOSFET, that is also known as NMOS. So you can see this is a symmetric structure, and you can replace source with drain and drain with source, and you can see this is substrate. Here I have taken the p type substrate, and this is the oxide layer, and this is a gate terminal, and this one is the oxide layer. This oxide layer is nothing as SiO2 layer, we can say, right? And you can observe here we have doped with n plus doping and n plus doping for source and drain, while the substrate I have taken here, we have taken here p type substrate. Now let's begin with the MOS structure. As this MOS structure, we can have 3 layers. The first one is the substrate layer, then SiO2 layer, and the gate layer, which is nothing but the metallic layer. So if I draw the energy band diagram of these 3 layers separately, then we have this is the energy band diagram of semiconductor material. There we have taken p-type semiconductor. So as you can see, this is a valence band, this is a conduction band, and this is a free space band we have. So the gap in between valence band and conduction band is known as the forbidden gap, right? So and as we know that for the pure semiconductor, the Fermi level lies just mid of the forbidden gap. So this is a Fermi level for the intrinsic type, but here we have taken the p-type semiconductor. That's why in the p-type semiconductor, Fermi level lies just above the valence band. So Here you can see here for the p-type semiconductor we have mentioned the Fermi level just above the valence band, right. So this is a energy band diagram of semiconductor, p-type semiconductor, and we have energy band gap 1.1 electron volt, because the forbidden gap for the silicon material always be the 1.11 electron volt. Next is a energy band diagram we have for the insulating layer, that is the SiO2 layer. So you can see there is a huge difference in between valence band energy and conduction band energy. Also we can call the forbidden gap is a very huge amount, that is 8 electron volt irrespective to the semiconductor material where we have 1.1 electron volt. So so the conduction the conduction cannot be possible into the insulating layer due to the having the very large forbidden gap. This is a insulating material energy band diagram. The next one is the metallic body. This is a metallic body, so this is a metal energy band diagram for the metal. You can see here the conduction band, valence band and Fermi level energy coincide with each other, and this work function uh, with the free space energy band is 4.1 electron volt. So these are the separately energy band diagram of the MOS structure. Make uh, if I for a device the Fermi level should be aligned throughout the structure. So in the next slide uh, we have uh, we have the energy band diagram of the combined MOS structure, where we have a metallic layer, oxide layer and p-type p-type semiconductor layer. So you can see the throughout the structure the Fermi level is aligned, right. EFM and this is a EFB is aligned throughout the structure, and you can see here at the interface of SiO2 layer and semiconductor layer, the band is slightly bending towards the downward direction, right. So this is a energy band diagram of a combined MOS structure. Then we will discuss the three mechanisms that will happen in the case of MOSFET. So first one is the accumulation, depletion and third one is the inversion layer. So first we'll discuss about the accumulation. So in the case of NMOS, we need to take the p-type as a substrate. So you can see here we have applied the negative gate voltage here. So if you apply the negative gate voltage, so p-type material has uh, majority carriers of holes while the minority carriers are electrons, right. So because you here we have applied negative voltage, so holes are attracted or accumulated at the interface of, this is the interface of SiO2 layer and semiconductor layer. So majority carriers, that is holes, are attracted towards the interface and accumulated at the interface. So a layer is generated, a layer is formed at the interface of majority carrier, and this accumulation of majority carrier is known as accumulation process, right. So here this accumulation can be happened by apply the negative voltage at the gate terminal only in the case of p-type. If we talk about the PMOS, then you have to apply the gate voltage, a positive gate voltage. So here we are talking about the NMOS, and the accumulation process is happening while applying the negative gate voltage, uh, right. The next one is the uh, this is a energy band diagram. As you can see here in the picture, because electric fields is going upward direction. That's why the energy uh, which uh, which in the MOS structure in the previous slide is bending, it is going upward direction clearly, right? So here in the accumulation process, at the interface of SiO2 and semiconductor layer, the uh, energy levels bending upward directions, right? In the depletion type, here you can see, here in the depletion type we need to give some small voltage at the gate terminal, then um, then the recombination process will happen at the interface of the SiO2 layer and semiconductor layer, as you can see here. So recombination, due to the recombination of electron and holes, only the immobile charge carriers will present at the interface, and the region where the only immobile charge carrier present is known as depletion layer. So this area is known as depletion uh, layer, and this phenomena, due to the apply of a small voltage at the gate terminal, will have a depletion process, right? So here you can see in the oxide layer the electric field is going downwards, that's why the energy level bending downward direction, as you can see here, downward direction at the interface of SiO2 and semiconductor layer. Now the third one is the inversion layer. So inversion layer, we need to give a little uh, uh, greater voltage as compared to depletion phenomena. So we need to get a large positive voltage at the gate terminal. So a layer of so more number of electron, that is minority carrier, attracted towards the interface of SiO2 and semiconductor layer. So more number of electrons attracted towards the interface due to the apply of this positive voltage. So a layer of a thin layer of electrons will be generated at the interface, and this layer is totally inverted with respect to the p-type semiconductor. So this layer is known as inversion layer, and this layer will be treated as a channel in between source to drain as well. So this is nothing but inversion layer, also known as channel in the case of MOS structure in between drain to source. So this is the energy band diagram for inversion layer. So you can see at the interface this uh, intrinsic Fermi level crossing the Fermi level of p-type, then we can say this p-type material will behave as an n-type material due to the crossing of intrinsic Fermi level at the interface of SiO2 layer and semiconductor layer. That's why uh, this phenomena is known as inversion layer, inversion process. Right. Next, operation of MOS transistor. So as discussed, there is no channel present in the case of MOSFET. So there is no channel, only a depletion region, as we discussed. At very small voltage, if we apply a small voltage as gate terminal, we have a depletion region, right? So this is a formation of depletion region. Then formation of inversion layer, when we apply a large voltage at the gate terminal, positive voltage, then we have an inversion layer, that is nothing but a channel in between source to drain, right? So this is n channel enhancement type MOSFET because we have created n type channel in between source to drain. So this is a formation of inversion layer. Then we have a linear region. So for the linear region, we need to apply a small BD voltage. If we apply a small BD voltage, electrons will travel from source to drain, right? Will attract from the drain side, and the current will, because the direction of current will be in the opposite direction of the flow of electrons, right? So direction of current would be from drain to source, right? So this is linear region, if we increase a voltage beyond some certain limit at drain terminal, so the at some certain point the channel will get deteriorates at the drain terminal and it will depleted at some point, and it has a zero width, we can say, and this phenomena is known as pinch off point, where we have a zero width of the uh, channel. So this phenomena is known as this voltage is known as pinch off voltage, and also known as saturation region or pinch off region, we can say, right. So beyond a certain BD, if we increase beyond the pinch of voltage, then channel will get decrease. As you can see here, channel is decreased uh, in between source through drain. So this phenomena is known as channel length modulation as well, because with the apply of voltage at VDS we can alter or we can modulate the channel. That's why we call this phenomena is channel length modulation we have, right. So this is a voltage current IV characteristics for the MOSFET. So you can see this is a linear region. At certain voltage we have some saturation uh, saturation region. This is saturation region, and the the locus of the pinch of voltage is always be a nature parabolic by nature. So this is a locus of pinch of voltage, right. So next is the basic operation and characteristics of depletion type N channel MOSFET. Previously we had discussed about the MOSFET, enhancement type MOSFET. So in this case we have a channel already present in the picture. So you can see here working phenomena is similar to the enhancement type MOSFET. This is the characteristics of this is a drain characteristics, and this one is a transfer characteristics. As you can see here, this is a saturation region, this one is a linear region, and the locus of the pinch of voltage is always be parabolic by nature. So you can see here, right. So uh, the, uh, this region, as you can clearly see here, this is a depletion mode. Depletion mode for if you give the BGS is negative voltage, then we have a depletion mode, and for the BGS for the positive value we have a enhancement mode, right. So this is a characteristics of MOSFET device, as we have transfer characteristics and drain characteristics. This is a depletion mode and this one is the enhancement mode. So overall we can say we have a two type of MOSFET, depletion type and enhancement type. In depletion type, channel is present, while in the case of MOSFET there is no channel present already. So we need to create a channel with the help of applied voltage at the gate terminal, uh, right. So in depletion type MOSFET we have both mode, depletion mode and enhancement mode, while in the case of enhancement type MOSFET only the enhancement mode will be present. So uh, so uh, we have N type and P type, D MOSFET and E MOSFET. So I think actually we have seen in throughout the lecture all the things will be controlled with the help of voltage. That's why we call this is a voltage control device, because we have, if we need to create a channel between drain to source, we need to apply voltage at the gate terminal, and we can control the current with the help of voltage as well. So this device MOSFET is known as voltage controlled device. So I think this topic is clear to all of you. Thank you.